Okay, so now we get to the heart of the equilibrium chapter, what we will call ICE tables, ICE tables, and there will be two types of ICE table problems. This is problem type 1. Given equilibrium concentrations, solve for Kc. And as it states, this is less than 10% of problems. And we'll start here, and then we'll work the other 90% of the problems. It says, for the reaction given here, the initial concentrations of nitrogen and hydrogen are 0.500 molar and 0.800 molar respectively. The equilibrium concentration of NH3 is 0.150 molar. What is Kc? So ICE table problems have a general form. They are going to have the reaction written right here. So this is going to be nitrogen plus 3 moles of hydrogen goes to 2 moles of ammonia. And up here, I'm going to have units. And so these units are going to be capital M for molarity. And that means everything I put in here will be in terms of molarity units. And then ICE stands for initial change in equilibrium concentrations. Initial change in equilibrium concentrations. And I'll write it out here, but then very quickly we will go to just writing ICE here. And then we put, so that's the basic setup. And for all ICE table problems, the 10% and the 90%, so I guess 100%, they'll all start like this. And every once in a while, you may see an ICE table problem with moles as the table, but most of ours will be molarity. Now it says the initial concentration of N2 is 0.500 and H2 is 0.800, and it doesn't mention anything about the initial concentration of ammonia. And that's very typical for this kind of problem because you usually start with no product, and since it doesn't mention it, it's another clue that there's zero concentration, zero product. We're doing this reaction then in the forward direction, and if we were to calculate from the previous video, QC would have a 0 in the numerator, and therefore QC would be 0, and QC therefore by definition is less than Kc. Kc, whatever it is. Anyway, so wherever there's a 0, the reaction has to go towards that 0 to create some of it. Now, this problem, it says the equilibrium concentration of ammonia is 0.150 molar. So I'm going to write down here 0.150 molar. We can do some lines in this table here. That's a good color for lines, just to keep things well organized. Okay, and now the way this works is that that's enough information to complete this table with all numbers. Because you can see if we start with 0 and we end with 0.150, then the change in concentration must have been plus 0.150 molarity. So, and that's just making the math work. But then we have to fill in the change in concentrations of these two. And what we know is that there's a coefficient of 2, 3, and 1 here. And mathematically, it's simplest to think of, well, if I made 0.150 molar ammonia, then how much did I take away? Well, it's going to definitely be minuses here because we're subtracting some of the reactants. And since it's a 2-to-1 ratio, you can see that if we call this x, or we call this 2x, even though we know it, then this would just be x. And so it has to be half of this value. And half of this value, I don't know why. That's what I thought, 0.075 is the amount that goes there. And so to make the 0.150, we must have reacted away half of that amount. and we must have reacted away 3/2 of the amount here, or 3 times as much, so it would be equivalent to 3x, and we know x. So now I'm going to take this number and multiply it times 3. I get 0.225. And now, if there wasn't a line here, even though there is, this is just straight subtraction. 0.5 minus 0.075 is 0.425. Here, 0.8 minus 0.225, 0.575. And what makes this problem different than the next one that we're going to do is that we now have all of these numbers, and we can now plug in and determine Kc. So Kc is products raised to coefficients over reactants raised to coefficients. I don't see any solids and liquids in here, but I do see some large exponents cubed there. So we have our equilibrium values. We can plug them right in. And not that we need units, because Kc values don't have units. I have a hard time not writing them. There you go. So let's see, 0.15. Oh, sorry, that 0.15 should be squared. I almost forgot that. Let me review the whole problem. I think I got all my exponents now. So squared divided by 0.425 divided by 0.575. And I'm going to have an x to the y, so raised to the third. And I get 0.063. How many sig figs do I have? I guess 3. 0.637 as my Kc value. Kc values are unitless. Actually, something doesn't look right there, so I'm going to redo this math the old-fashioned way. So 0.150 squared divided by 0.425 divided by, 0.575 divided by 0.575 squared. I don't know what happened there. 0.278. That is the correct answer. I'm not very comfortable with the x to the y button there, so that is the right answer. So that's the first type of problem. Not too bad. It's our first ice table, and this would be what could be called an ice table with all numbers, because from the problem statement we could put in all numbers right away. And that's also called solving for Kc type of ice table problem. Now this is problem type 2. It says, given Kc, solve for equilibrium concentrations. And we have a different reaction, have a Kc value at a temperature. If concentration of PCl5, which is our reactant, equals 5 molar initially, and we're assuming that there's no concentration of products, calculate the equilibrium concentrations of all species. So here's given Kc, solve for equilibrium concentrations. But this is also an ice table problem, so we'll set up our ice table. Although this takes significantly more work, and so there is another page after this one. So we have a molarity, we have a reaction. We have our initial change, and pretend our paper has lines. And for me, when I fill this in, I always try and write the Kc value right here. Kc equals 85.0. I I know that I have 5.00 molar initial, no mention of products, and so we assume they are 0, and that is a good assumption. It's an assumption you can always make if there's no information about the products. Now, what's clear is that the reaction has to go to the right to generate products. Our QC, if we calculated it, would be 0 and be less than KC. But what's not clear is how much of this reaction occurs. So I'm just going to, but since it has to occur in the forward direction, I will put minus x here, and I will put plus x and plus x. And since all of these coefficients are 1s, it's like all of these have 1x, minus 1x, plus 1x, and plus 1x. And now we have to write out our equilibrium values in terms of x, and that's what we're going to solve for, because these are our equilibrium concentrations for what it's asking. Okay, so good. Now we take our Kc and we write out our equilibrium constant expression. It's products raised to exponents over reactants. And then I'm going to plug into this expression. I know my Kc value, it's 85.0. I know each of these are x for my numerator, so x, x. And I know my denominator is 5.00 minus x. So that is the equation we now have to solve. It takes a little bit, but we will do it. Let's do 1 or 2 steps up here. So this is, I'm going to cross multiply. And therefore I'm going to get 85 times 5 minus x equals x squared. Then I'm going to multiply this out. So 85 times 5 is 425. And I'm going to drop my zeros here, but I do have 3 sig figs for these. So that's just going to be 85x equals x squared. And this is a quadratic, so second power polynomial. I don't know, somewhere in there there's the right math term. And the way to solve this is to get it into the correct form, to use the quadratic equation. You will have the quadratic equation on all of your conversion and equation sheets moving forward. The proper form looks like this. It's got to be x squared. Well, let's see, I'm going to put everything over on the other side. So 0 equals x squared. And both of these, when they move over to the other side, will have opposite signs. Plus 85x minus 425. And then the number here is called A, B, and C. And the quadratic formula, believe it or not, we are going to use it and solve. So x equals minus b plus or minus b squared minus 4ac under the root symbol there over 2a. And let's go ahead and solve this. So minus b is going to be minus 85 plus or minus b squared 85 squared minus 4. A is just 1. We'll put the 1 in there. And C is minus 425. Put that all over 2A. And A is just 1, so it's just 2. So now we have that because there are 2 roots. There are 2 roots plus or minus. Let's go ahead and solve that now, slowly but surely. So let's see, 85, oh, clear it. 85 squared minus 4 times this, which this is going to be positive, so it would end up, I'm just going to add it, plus 4 times 425 So I get minus 85 plus or minus square root of 8925 over 2. And what you can see is because this term became positive, so this term is going to be larger than the term that we've got here. Anyway, so square root of that is 94, so 85 plus or minus 94 point, well, we'll keep 3 sig figs. That should be plenty for now. Divided by 2. And our two roots are going to be, well, I'll take the positive root first, 94.5 minus 85 divided by 2. I get 4.75 molarity. And another one, it's going to be negative, but 94.5 minus 85 divided by 2. Yeah, minus 89.8 molarity. So one of these roots will be physically possible, one of them will not. So this one is not a real answer to this problem. This one does make sense because we can only take away less than 5. Oops. We can only take away less than 5, so 4.75 is a possible answer that makes sense. The other one is not. So now let's come back. So we solved for x. We come back, it says calculate the equilibrium concentrations of all species. And what you can do is you can actually come back here to your problem and say a second E, and then 5 minus 4.75, there we go, is going to be 0.25. And then these are just going to be 4.75 molarity. And those are your equilibrium concentrations. And another thing that's really nice about these problems is they're self-checking. So what I mean by that is that we know that Kc equals 85. We know that if we multiply these two numbers and divide by our reactant concentration, we should get 85, or something very close. Let's see what we get here. So 4.75 squared divided by 0.25. You can see I get 90 here. And whenever you do multiplication and division of numbers with small differences, so you're going to get something very close. So getting it equals 90 is close enough. So if you got something that was 250, you would worry. And I have set the answers on the homework to recognize this fact, just so you know. So 4.75 is fine. And we are now done. This is our first ice table problem. We will do many of them, not as many as the limiting reactant problems we've done and will do in this course, but a lot.